Hello everyone. Good morning and welcome you in the ACM Inter School. So today we are going to learn from Supratik regarding the reactive synthesis. So before that, I'm just wanting to introduce our speaker. So Supratik is a Bajaj Group Chair Professor in the Department of Computer Science and Engineering at IIT Bombay, where he is also a principal investigator in the Center for Formal Design and Verification of Software. He received a BTech from IIT Kharagpur, an MS and a PhD from Stanford University, and spent a year as a member of research staff at Fujitsu Laboratory of America before joining IIT Bombay. So Pratik's research interests include constraint sampling and counting, formal verification, automated synthesis, automata theory, and logic. He is particularly interested in the development of a scalable algorithmic technique with a strong guarantee for reasoning about different computational models. He is a fellow of the Indian National Academy of Engineering and is a distinguished member of ACM. And now stage is yours, Supratik.
Yeah, thank you, Avanish, for the kind introduction, and good morning, everybody. So, yeah, I don't know if turning on the video is going to, utilize the bandwidth less optimally, but maybe I'll turn it on for some time so that at least you can see who I am. Uh, and then maybe as we go, yeah, it's more important to see the slides than to see who I am. Okay, so good morning, and what I'm going to talk about today is on this topic of reactive synthesis. Now, this is actually a very vast area of study, and there is an enormous amount of work that has already happened. And in trying to prepare for today's tutorial, I realized that given the time constraints, it is going to be absolutely impossible to even introduce you to the various ideas that have turned out to be important in this area over the last almost 5 decades. Uh, so what I'm going to do today is I'm going to first hopefully you know be able to tell you and make you understand what reactive synthesis is. At least that we should know. What is the problem we are trying to solve? And then we are going to try to see a few basic approaches, very fundamental approaches to solve this problem. And hopefully I will also be able to give you some idea of some of the more modern approaches uh, which have been found to be more efficient in practice than the fundamental approaches. And then in the last session, we will have a hands-on session with one of the best tools that is around for reactive synthesis. Okay, so let's get going. So, what do we mean by synthesis? And, at a very high level, what I would say is that suppose I told you that a certain work needs to be done, right? So, suppose I told you that I have a set of numbers and I want these numbers to be sorted. So I told you what has to be done, but I have not told you how it is to be done. So the process of synthesis is to automatically derive a way to do the task starting from a description of what the task should be doing, right? So a description of what the task should be doing is often called the specification, and a system is typically how the task is going to be done, but this is to be designed, this is not given to us. So my specification could be saying that the output list of numbers or the output sequence of numbers should be sorted. The system to be designed should take in a set of numbers and it should produce an output sequence of numbers such that the output sequence of numbers is sorted. Now, sorting is just one simple example I gave because this is perhaps familiar to most of us. A more interesting example might be that, just think about uh, let's say that we are trying to design a self-driving car, or we are trying to design a robot that must navigate itself in some uncertain territory, right? So we would like to design maybe some software, maybe some firmware, maybe some hardware, doesn't matter, some system which is going to satisfy some basic specifications. For example, if it's a self-driving car, maybe we want to make sure that it doesn't go and collide with some other car. Of course, how does one specify this in English language? It's easy to say it doesn't go and collide with another car. So we will see that there are limitations of the specification language that we use, but ideally we would like to say this, that I want to design a self-driving car that doesn't go and hit anybody, or I want to design an autonomously navigating robot that doesn't go and bang against some obstacle in the arena where it is navigating itself. So in all of these cases, whether it is the sorting or the self-driving car or the autonomously navigating robot, uh, it's it's relatively easy to say what we want the system to be doing than to actually design the system. And this is why synthesis or automated synthesis is an important problem, because often it's easier to say what do we want to be done rather than how is it to be done. Okay. Of course, as I said, the language that you use for the specification puts in constraints, and sometimes we are not able to even specify exactly what we want. For example, how do we specify in a very rigorous way that a car should not go and hit another car? Uh, so there are limitations of that. But I mean, this is the overall goal, that it's it's often relatively easier to say what we want to be done uh, rather than saying how it is to be done. And we would like an automated way. I mean, it would be really wonderful if we had automated techniques to go from the requirement specification to the actual system design. If we had this, then perhaps we would not need any programmers anymore. We could just specify what the program should be doing and press a button, and out should come the program. But of course, we are far, far away from there as far as generic programs are concerned. For special classes of programs, this can indeed be done. So with that very high level description of what synthesis is, I want to formalize this a little bit more, because that will be helpful for our purposes as we go along. So I want to say that the requirement specification should be a formula in some logic. You can choose whatever. I mean, you've already had a session on logic, so you can choose whatever logic you want. So our requirement specification should be a formula phi in some logic, and the free variables of this formula could be the inputs to the system and the outputs of the system. And we'll shortly see a few examples of how we can write such formulas. But once we write such a formula in a given logic that relates the inputs and the outputs of the system, this gives a fairly precise mathematical definition of what is it that we want about the relation between the inputs and the outputs. The inputs and the outputs should basically make this formula true. So given a set of inputs x1 to xn, let us say, my system should generate outputs y1 to ym, such that when I plug in the values of the given inputs and the generated outputs, this formula should become true. So that's our slightly formalized view of what we want the system design, what we want this automated system design or automated synthesis to be. So our goal is to automatically synthesize the system such that this specification represented by this formula is satisfied. Now we will soon see that uh, it is, if I give you an arbitrary formula like this on some input variables and output variables, it may not be possible to design any system, any realistic system, which can actually satisfy that specification. So we will add this extra rider to it, saying that we want to automatically synthesize the system such that it satisfies the specification, but whenever possible. And if you give me a specification such that it is not even possible to design such a system which satisfies that specification always, then of course there's not much we can do. Okay, So in general, what should the system do? So the system could be a program, could be a hardware state machine, could be a mixture of software and hardware, whatever your favorite uh, style of design is. But in general, whether you write it as a program or a piece of hardware or a mix of hardware and software, what we are saying is that we have to look at these inputs and we have to generate these outputs. But of course, the system can internally remember something about the past inputs and outputs that it has seen. So we need the y's as functions of the history of x and y, which can be summarized perhaps in some state of the system. But anyway, that state does not show up in the specification. That is internal to the system. That depends on how you design the system. So the specification just talks about the inputs and the outputs. And the system to be designed uh, is going to generate the outputs, definitely taking into account the inputs, but it may also take into account the previous history of inputs and outputs of what has happened. And so it may have some states, but these are hidden. The specification does not talk about these states. Okay, so let me just try to now make this concept a little bit more concrete by walking you through a few examples where we'll see the different kinds of things that can happen. Okay, so suppose, I'm given to understand that you have already been introduced to LTL, linear temporal logic. So that is correct, right? Linear temporal logic has been introduced. Can somebody confirm? Okay.
Yes, sir.
Okay, great. Yeah, so I would like to hear things from the other side as well, because otherwise it's not clear to me whether I'm speaking just to a computer or to human beings. Uh, so, so here is an LTL specification of a system with two inputs and two outputs. And, since you are already familiar with a little bit, at least, with LTL syntax and semantics, so I will just sort of try to explain what this formula is trying to say, and then you can let me know if you think your interpretation is different, right? So what this formula is saying is that as the system runs, at any point of time, so this is globally, so at any point of time, if x1 becomes true, so let's say these are all Boolean variables, x1, x2, y1, y2, at any point of time, if x1 becomes true, then at a future point of time, y1 must become true. Okay? So if x1 is true, then eventually y1 will be true. And this is true at every point of time. So if now x1 becomes true, then at some point in the future of now, y1 will become true. If 10 time steps later again x1 becomes true, then sometime in the future of that 10th time step again y1 will become true, and so on and so forth. So it doesn't say when y1 should become true after how many steps, but it says sometime in the future. And this is a similar statement about x2 and y2. So it's saying that if whenever x2 becomes true, at some time in the future of that instant, y2 will become true. And this is saying that at every point of time, either y1 or y2 is false, which means at no point of time can you have both of them as true. Okay? So if you think about it a little bit, this is actually some kind of a rudimentary specification of an arbiter, right? So let us say that uh, you have a common printer that two users want to use, and this is the arbiter you want to design, and these x1 and x2 represent requests for using the printer by the two users, and these y1 and y2 represent who has been granted use of the printer. So if y1 is true, then user 1 can use the printer. If y2 is true, then user 2 can use the printer. So you definitely don't want both user 1 and user 2 to be using the printer at the same time. And you want that whenever user 1 has requested for the printer, at some point in the future of that instant, user 1 will be granted the use of the printer, and similarly for user. Okay. So this looks like an interesting specification. It's talking about a very simple arbiter, two input, two output. And note that this specification is not telling us how should we design this system. This is just telling us what is the relation we expect between the inputs and outputs of the system. One thing to note in this specification is that it has temporal operators, right? So it has G and F and all of those. And if I hope you're already familiar with the syntax semantics of LTL. We will actually cover a little bit of that very, very quickly, shortly. But from whatever you have already studied, it should be clear that this specification, because it has temporal operators, it is actually not relating the values of x and y at one point of time. It is probably relating the values of x and y across different points of time. So it relates sequences of x and y values, right? It may need to look into the future, for example, right? This fy1, fy2, and so on. So here is, you know, a rather arbitrary choice of a sequence of valuations of x and y that can happen if I were to design a system that satisfies this specification. Okay. So maybe we start off with x1 and x2 being 0 and y1 and y2 being 0. And then at the next time instant, x1 becomes 1. Well, so our specification says that at some point in the future of this time instant, y1 should become 1. But it doesn't require y1 to become 1 immediately. So maybe in the next time step, y1 has become 1. But maybe by the next time step, x1 has become 0. But that's okay, because since x1 was 1 here, y1 has become 1 in the future of this time instant. Okay. And although both x1 and x2 were 0 here, it's perfectly fine for y1 to stay true over here in the next time instant, because nowhere does it say that if y1 is true, then x1 must be true at that same time instant, right? So maybe y1 is held true over here, but in the next time instant, x2 provides a request. So this becomes 1. And then we know that sometime in the future, y2 must become true, but then y1 and y2 cannot become true at the same time. So maybe at the next time step, y2 becomes true and y1 becomes 0. And maybe in the next time step, again, x2 becomes true, and y2 stays true. So this is just an example sequence of valuations of x1, x2, and y1, y2 that can happen if somebody were to magically give you a system that satisfies this specification. Of course, in this case, we are saying that the moment x1 came, in the next time step, y1 came. A system that satisfies the specification does not have to meet this. I mean, y1 can come anytime in the future. Here, for example, when x2 came, y2 was already true at that point. It doesn't have to be that way. Y2 can be true at some time in the future. But this is just an example sequence. Okay. Is this clear to everybody? I mean, is this specification illustrated through this sequence of valuations clear to everybody? I need some response from the other end.
Yes, sir.
So it's Rohan only who's talking. I'm not sure. Okay, so maybe I'll just ask specific participants. So, Bhaskar, Vyas, are you there?
Yeah, it's clear.
Yes, sir, definitely.
Yeah. So was it clear what I mentioned about LTL?
Yes, sir, I'm still checking it out. Like,
Okay. Shruti Priya, are you there?
Hello.
Yeah,
Yes, sir.
Shruti. Yeah. Was it clear what I mentioned?
Yes, sir.
Okay. Okay. If it is not clear, please stop me, because I think it's much more important that we understand what we are studying rather than trying to study too much without not understanding everything. So, so if you agree that this is a likely sequence that can come out of a system which may be synthesized automatically starting from the specification, you will notice a few interesting things here, right? So, for example, note here that x1 and x2 are both 0 and y1 and y2 are both 0. But here x1 and x2 are both 0 and y1 and y2 are not both 0. This is 1, this is 0. And here is another instance where x1 and x2 are both 0 and y1 is 0, y2 is 1. So clearly the values of y1 and y2 are not getting generated just by looking at the current values of x1 and x2. Okay? Because the same 0, 0 on x1 and x2 are producing different values of y1 and y2. while meeting the specification, right? So what this says is that y is a function, the values of y1 and y2 is a function of course, it has to be a function of, it has to take into account the current values of x as well, but perhaps it should also take into account what has happened in the past, the history of x and y. And the moment you see this, the reason I gave this example is for you to clearly see that here I cannot possibly talk about y1 and y2 being generated just looking at the current values of x1 and x2. I have to look at, for this y1 to be equal to 1 over here, I have to remember that x1 was set to 1 sometime in the past. Otherwise, there is no reason for y1 to be 1 over here. Y1 could as well have been 0, like it was over here. Okay. So if the outputs have to depend on the state which summarizes the history, past history of inputs and outputs, and the current value of the input, then this actually starts sounding something like a finite state machine. I've talked about a Milli machine here. You can also use a Moore machine. Milli machine is the one that we will be using for our purposes in this in today's tutorial. So, but it's basically a finite state machine. Takes as input x, outputs y, and then there are hidden state variables that are remembering this history, but they are not part of the specification. Okay, so this gives us our first idea that okay, maybe what we have to do is, starting from the specification, we have to figure out what kinds of sequences can be satisfying the specification, and from that sequence, from that entire set of sequences that can satisfy the specification, we'll have to figure out how to determine y in terms of x and some notion of state that summarizes the history of x and y. Okay. So this was one example.
Uh,
Yeah. Go ahead.
so in this case, I don't see any kind of difference between y and the current state of x. Neither the specification nor the valuations point to that.
There is no difference between y and the current state of x.
Sorry, y does not depend on the current state of x, current value of x.
I mean, for example, here it does, right? Here x2 was 1 and y2 immediately became 1. So in the next state, for example, it is okay for y2 to be 0. So this notion of future in LTL includes the present time point.
Right, okay. So greater than or equal.
Greater than or equal to.
Right, okay. But then, yeah, now that you mentioned that, would you consider the last valuation to be, so the last two valuations both have y2 equal to 1. So would you consider that a state change? Would you consider that a change in the value, or would you just consider it to be a constant? Like it did not change.
Change in the value of what? In the value of y2?
Yeah.
No, y2 has been held constant, but the reason y2 has been held constant may be different here than here. The reason why y2 is 1 here is that x2 was 1 here.
Yeah, that is true.
The reason why y2 is 1 here is perhaps x2 is 1 here.
Right, but you can't say that for sure, right?
This is just some arbitrary sequence satisfying this I have picked up. It depends on how you implement the system. For example, it's perfectly okay for you to. So here is here is a very naive implementation of a system that will satisfy the specification. Suppose I have a system which alternately grants y1 and y2, right? So it first makes y1 true, y2 is false, and then in the very next step it makes y1 is false, y2 is true, and then the very next step it again makes y1 is true, y2 is false. So it doesn't even look at the input. It just keeps flipping y1 and y2 alternately, right? You will see that that system also happens to satisfy the specification, because certainly y1 and y2 are not being true simultaneously, right? And if you did make x1 true, then sure, you may have to just wait for one more cycle for y1 to become true, because y1 and y2 are just, happening alternately. And whenever you make x2 true, maybe you have to just wait for one more cycle and y2 is true, right? So that could be yet another implementation, and that's perfectly well satisfies the specification. And you see the kind of extremeness of that implementation, because it doesn't even look at the inputs. It just is flipping the outputs back and forth, and it satisfies the specification, right? So if this was your specification, then that is fine. Now, if you say that, no, I didn't really want to have this. I mean, if y1 has got to be set to true, then at some point in the past, x1 must also have been true. Then you have to add that to your specification. You have to say that, well, if y1 is true here, then at some time in the past, there is linear temporal logic with past operators. You may not have studied that, but there is linear temporal logic with past operators, and you can use that to specify, for example, that at any point of time, if y1 is true, then at some point of time in the past, x1 should have been true. But unless you put that in your specification, even this very degenerate implementation which just keeps flipping y1 and y2 without even looking at x1 and x2 is also a correct implementation that satisfies the specification. Right? So I have just shown one possible thing that I just cooked up over here. It depends on what the system you're actually designing. Does that answer your question?
Yes.
Yeah.
Excuse me, sir.
Yeah, go ahead.
For the last part, when you see the y2 is 1, you said it's because x2 is 1 in the present only, right? Here you are not seeing the past. So when you are making it, like when you have a temporal logic, like x2 implies future of y2, right?
Yes.
But here you are seeing the present also. So is it applicable just in the final state, like the final sequence, or?
No. So okay. So we will go over this again. So if you remember from, I think on Monday, Sunil Simon had introduced LTL to you.
Yeah.
So the meaning, the semantics of the future modality or the future operator is that it is this time instant or sometime in the future. So this F in temporal logic includes the current time instant. Okay. If we want to exclude the current time instant, if we want to say that y2 must not be true at the current time instant, but y2 must be true at some time instant ahead in the future, then you have to say that negation y2 and fy2. So that says that y2 is false currently, and y2 has to be true either at the current time or at some time in the future. But since we have specified y2 has to be false currently, it forces y2 to be true strictly in the future.
Yeah. Okay.
Did that make sense?
Yes.
So it depends on what you have written down in the specification over here, right? If I had written x2 implies negation y2 and fy2, then this would not satisfy the requirement that this y2 is responding to this x2. There would have to be another state. Since you mentioned that this is the final state or the terminal state, there is nothing like a final state or terminal state here. I have just taken a snippet from a hypothetical implementation of the system. And there are, of course, states after this, there are states before this and all of that. Okay, we'll come to that. I mean, we are actually not talking about systems where there are necessarily end states or termination states. But it's just a continual interaction between the system and the environment. Okay?
Yeah.
Okay, great. So good. Very happy to hear questions from some of you. I hope the others will also be encouraged to ask questions. But now here is a very interesting specification. So here, I'm sure you would have studied on Monday that there is an operator called the next operator in linear temporal logic, and usually it is denoted by the X symbol. But then when I was preparing these slides, I noticed that my input is also called X, and this was looking very funny. It was looking XX and this was looking XXX. So I said, okay, let's just say next X and next of. Okay, there's a missing parenthesis here, closing parenthesis. Okay, so this is a linear temporal logic specification, within the syntax of LTL. And this is specifying some relation between a single input and two outputs. So I want my system which has a single input and it has two outputs. Okay? And what is the specification saying? Right? So this is saying that the current value of y1 should be the same as the next value of x, and the current value of y2 should be the same as the value of x 2 steps down the line. Is that clear? Right? So next of x would be true at the current point of time if x is true at the next point of time. So since next of x has to be equivalent to y1, y1 has to be true at the current point of time if next of x is true at the current point of time, which means if x is true at the next point of time. So y1 is true at the current point of time if x is true at the next point of time. This is saying y2 is true at the current point of time if and only if next of x is true, right? Now what is next of x? So when does next of x become true? When x is true at the next point of time. So when does next of x becomes true? When next x becomes true at the next point of time, which means when x becomes true. If the current time point is t, next of x becomes true if next x becomes true at t plus 1. And when does next x become true at t plus 1? If x becomes true at t plus 2. Okay? So this is saying y2 is true at time t if and only if x is true at time t plus 2. So as an LTL formula, there is nothing wrong about this formula. This is meeting all the syntax requirements. There is a clear semantics for this formula and so on. But if I try to list out, or if I try to do the same exercise that I did in the last slide for the x value and the y1 and y2 values here, I'm going to get something like this. Okay, so maybe I start off by saying, not even start off, maybe at some point of time, I have x is 1, y2 is 0, and y1 is 1. But remember, the value of y1 must match the next value of x. So if y1 is 1 here, then the next value of x should be 1. And the value of y2 should match the value of x 2 steps down the line. So if this y2 is 0, x 2 steps down the line should be 0. Okay? But if this is 0, then y2 here should match x in the next step. So this y2 should be 0. And this y1 should match x 2 steps down the line. So if that is 0, then this will be 0. Right? Similarly here, this, y2 here matches 2 steps down the line and y1 matches 1 step down the line. This y2 matches x 2 steps down the line, y1 matches x 1 step down the line. Right? And this y1 matches x 1 step down the line, y2 matches x 2 steps down the line. So as I said, this is really an infinite sequence. I've just taken a snippet and I'm showing you the snippet. So, so is this clear? I mean, given this LTL spec, which is a perfectly legitimate LTL spec, I might have a sequence of valuations of x and y like this. And then we need to ask that, well, can we at all design this system? Because there's something funny happening here, right? I mean, x is my input and y is my output. The y1 and y2 are my outputs, right? So if I am required to generate the value of y1 here at the current point of time, such that it matches the value of x at the next point of time, I mean, how do I even know the value of x at the next point of time? And this y2 must match the value of x 2 steps down the line. I mean, how do I know at the current point of time what will be the value of x 2 steps down the line? So there's something funny going on here. And if you think about it a little bit, can I get some responses from the audience? Do you think that the system can be designed? Can I design a system which will match the specification? Any system that matches the specification. Yes, anybody?
Is this some sort of a sequence generator, sir?
No, this takes inputs and produces outputs. So it takes a sequence of inputs and it produces a sequence of outputs. At every step, it looks at some x, generates some y1 and y2. Again, the next x comes, it generates some y1 and y2. But of course, as we said, that this system is allowed to remember something about the history. Right? Because if it has seen something in the past, it's allowed to remember that. In fact, we saw that was important in the arbiter example, that it needs to remember something. But here we have a specification. I'm starting from a specification for which there at least seems to be a problem, when I look at this, because at the in trying to generate y at the current point of time, I need to know the value of x at some future point of time. But at the current point of time, how do I know what inputs are going to come in the future point of time?
I can actually think of two situations here. One could be that we constantly keep all xy1 and y2 to be the same value throughout. That
No, but
could be.
x is an input. You don't have any control over the input. You are designing this system.
So there is no way to restrict the kind
Absolutely
of input.
no way. X is an input coming from the environment.
Yeah, but there has to be some domain.
No, so you have no control over x. You can only control y1 and y2. I mean, think about it. Right at the beginning, what I said, right? Maybe you're given a list of numbers, and your requirement is to sort them. You have no control what list of numbers is going to come to you.
Correct. Okay. Yeah. One other thing could be that there is some kind of table.
Like
Eh?
some kind of starter set or something.
I can't hear you clearly. Can you speak up?
Yeah, like some type of starter set or something. Like it will need a set of initial conditions, like to establish the loop, like sort of like because it's going three steps in advance, right?
So you're saying some kind of loop.
Yeah, like I mean, it might need some set of values to begin with, right? Values and then results, like Rahul said, like sort of like a truth table or something.
Okay, so let me. So it's good. Let us discuss this.
Can we peek at the input like later inputs?
Yeah, so that's the problem, no? So let me just share my other screen where I can write. Maybe I should have. Second. Yeah, can you see my screen?
Yes, sir.
Yeah. So I mean, let's see what we are talking about over here, right? So okay, just give me a second. I forgot to connect my. So yeah, should be fine. So, okay, can you see my screen?
Yes, sir.
Okay, great. So so what I'm saying is, oh, okay, I'll just use the mouse. It's working until this morning. So I want to design my system which takes X as input, right? And it generates Y1 and Y2 as outputs. Okay. So X is here and Y1 and Y2 are here. Okay, so and let us say that this is time and this is time 0 and then time 1 and then time 2 and so 2 and 3 and so on. So let us say the input, I mean, I have no control over the input, right? So let's say at time 0, I got the input 0. Now at time 0, I have to generate some value for y1 and I have to generate some value for y2. So what value should I generate for y1? I have got the input 0. what value should I generate for y1? So there are two possibilities, right? Either y1 can be 0 or y1 can be 1. So suppose my system generates y1 is 0. Then, because the input x, I have no control over it. Suppose the next input that comes is 1. Then I have violated the specification, right? Because y1 at the current point of time must equal x at the next point of time. So y1 cannot be 0. Because if y1 is 0 and I have no control over the input, and if the environment is an adversarial environment and it provides the input 1, then I'm forced to violate the specification. Whatever system I have designed, which was generating y1 as 0 at the first step, looking at x is 0 at the first step, will be forced to violate the specification, because the adversarial environment can provide x as 1 at the next step. So we say, okay, y1 can't be 0. So then what can y1 be? Then y1, it's either 0 or 1. These are binary outputs. So we say, okay, then y1 must be 1. But then if y1 is 1, the adversarial environment now will provide 0 as the next input. And once again, it has forced me to violate the specification. Do you see the problem? So at time point 0, I have to provide some output y1 and y2 such that, and again at time point 1, I have to provide some output. At time point 2, I have to generate some output such that the sequence of inputs and outputs satisfies the specification that we had written, right? The specification was that globally, next x is y1 and globally next of next x is y2. So this was my specification. And no matter what system I design here, it has to generate some output at the first time step. But we have just argued that no matter what output it generates, whether 1 or 0, an adversarial environment can force the system to be violating this specification. Is that clear? Is this argument clear?
Yes, sir.
Right. So basically, this is a specification which poses a genuine problem in terms of synthesizing the system, because it looks like no matter what I do, no matter what system I synthesize, the environment can provide a sequence of inputs that will make me violate the specification. As opposed to the previous case of the arbiter, where I could design a very simple system which was just alternating between y1 being true and y2 being true. And then no matter what input the environment provides, the specification is satisfied. Right? But here it looks like no matter what system I design, the environment always has a way of providing a sequence of inputs such that the specification is violated. Right? So does anybody not agree with this? Okay, so I don't know what that silence means. Okay, so therefore, what we are talking about is a situation where let me share my original screen back. Yeah. So we're talking about a situation where this system looks like it cannot be designed. No matter what I do, the environment always has a chance to make the system violate the specification. So I cannot design this system such that for all sequences coming from the environment, it will meet the specification, which is very different from the situation we had earlier, where if this was the specification, I can actually design a system. And in fact, I can design a system which doesn't even need to look at the inputs, which will always satisfy the specification no matter how the environment is sending the inputs. Okay, so do you see the difference between these two cases? So indeed, in this case, this specification is unrealizable. It means that it's not possible to design such a system, because I need to look into the future. In order to generate the value of y1 now, I need to know what the value of x will be at the next time step. But I cannot look into the future because the value of x at the next time step is in the hands of the environment, and I don't control the environment. Is this clear?
Yes, sir.
Okay. So, what this means is that this is actually, I guess, I mean, 50 minutes into our session, we are already seeing that we are perhaps trying to attempt something impossible, that there will be specifications that for which we cannot design systems. No matter what system we design, it is not possible for the specification to be met for every input sequence, right? But nevertheless, there are interesting specifications like this arbiter for which I can design this. So yes, this problem is of the nature that not for all LTL specifications you may be able to design a system that meets the specification for all sequences of inputs that come. But if the system is realizable, which means that if indeed there exists even one system that allows you to meet the specification for all sequences of inputs that comes, it will be very much worthwhile to try to see how we can generate that system automatically. And of course, it will also be worthwhile, given a specification, to be able to come up with an answer saying that, no, the system is not realizable, don't try to realize the system, because the environment can always beat you. Okay. So it's important to answer the unrealizability question given a specification. Is it realizable or unrealizable? And if it is realizable, it's certainly important to try to automatically generate a system that satisfies the specification for all sequences of the inputs. Okay. Now I want to present a third example, and this will be the last example to motivate what we are trying to do. After that, we will try to get into the nuts and bolts. So this example also has one input and two outputs, and you look at this specification. So this is a specification, as I've written, it's a bit vector specification, which can of course be written down as a propositional specification. What it means is that, what I mean by this bit vector specification is that X is a bit vector, Y1 is another bit vector, Y2 is another bit vector. Okay. So you can think of X as being 2n bits, y1 as being n bits, and y2 as n bits, right? So the number of bits in X is twice the number of bits in each of y1 and y2. And the specification says that for an X, the y1 and y2 that you generate should satisfy this. What is this formula? This formula is saying X as a 2n bit vector should be equal to y1 as an n bit vector multiplied by y2 as an n-bit vector, and this subscript of n means this is the n-bit multiplication. Okay, so it's saying that X should be the product of y1 and y2 in bit vector arithmetic, and y1 should not be equal to 1 as an n-bit vector, right? Remember, y1 is an n-bit vector, so y1 should not be equal to 1 means 1 represented as an n-bit vector, y1 should not be that. And similarly, y2 should not be 1 represented as an n-bit vector. So once again, you look at the specification and you say, okay, I think this clearly, tells us what is the relation we need between the inputs and the outputs. And note that this specification has no temporal operators. It's just relating the present value of X to the present values of y1 and y2. So I could have a sequence of valuations of X, y1, and y2. So as I said, these are bit vectors. So I will represent them using the unsigned integer that they represent. So maybe initially, if X is 15, then y1 and y2 can have the values 3 and 5, of course, as bit vectors, right? And then you see that this specification is satisfied. Indeed, 15 is equal to 3 times 5, and y1 is not 1 and y2 is not 1. Maybe at the next time step, X comes as 24 and the system generates y1 is 8, y2 is 3, again fine. 51, 3 and 17, it's fine. Again 15, and of course it could have generated y1 as 5 and y2 as 3 at this time. That would also satisfy the specification. But if it generates y1 as 3 and y2 as 5, which is basically this same combination of inputs and outputs again, then also the specification is satisfied. What happens if I feed z? If I feed the value of x as 7? Okay. Now, is it possible to get two numbers y1 and y2 such that their product will be 7, but none of these numbers are individually 1? I'm basically asking, can 7 be factored into two parts, none of which are 1? Right? Can this be done? Can 7 be factored into two parts?
No.
No.
No, right? 7 is a prime number. So then what happens? So, if x comes as 7, I mean, my system should generate some output, but we know that for x is 7, there is nothing. There is no value of y1 and y2. There is no correct value of y1 and y2, which will satisfy the specification. So in such cases, we may be okay taking garbage on the values of y1 and y2, because for 7, there is really no value of y1 and y2 that satisfies the spec. And so and you have to generate some value for y1 and y2. No matter what you generate will violate this, so you might as well generate something arbitrary. But whenever x is again a value that admits factorization, non-trivial factorization, then we again expect. So in general, I can have that this was 8, this was 3, and now this can become 3, this can become 8, and so on. I mean, in general, all of this satisfies the specification, right? But now what we can see is that if I look at this specification, since it is relating the present values of x to the present values of y1 and y2, absence of temporal operators. So it is indeed possible to design y1 and y2 as functions of x, like a combinational circuit. Okay? If the present value of x, it generates the present values of y1 and y2. No history is needed because it looks like this specification is just relating the present value of x to the present values of y1 and y2. It doesn't care what had happened in the past. Okay, so if you give us 7, there is no value of y1 and y2 that you can generate which will satisfy the specification, and it doesn't matter what had happened in the past. And similarly, if you give a 51, you can indeed generate y1 and y2 that satisfies the specification, and it doesn't matter what had happened in the past. So once again, this is unlike the previous two examples where we saw that there were temporal operators. I needed to refer to values at some other points of time, not just the current point of time. And so in such cases, if I'm just referring to the current values, I can indeed think of at least try to generate y1 and y2 just as combinational circuit, no hidden state variables. But even then, as you can see that there might be inputs for which you can't generate the correct outputs. So in some sense, this is an unrealizable specification because not for every value of x can you generate the right values of y1 and y2. But nevertheless, we've just seen this, that if x is prime, you can't generate y1 and y2. So technically, this is an unrealizable specification because the environment always has a way of providing an input such that no matter what you do, the specification will be violated. But yet you see that even when a specification is unrealizable, it's sometimes useful to design systems such that a specification being unrealizable just means the environment has some adversarial input that it can provide, which will make you violate the specification. But maybe there are other inputs that the environment can provide for which you can actually satisfy the specification. And this particular example is something like that. We are basically doing factorization when the number can be factorized. Because if the number cannot be factorized, then you can't do the factorization. So even when a specification is unrealizable, it may be useful to synthesize a system that works on only those inputs that come from the environment for which it's actually possible to design, it's possible to generate outputs that satisfy the requirement. Okay? And of course, you see that if I could actually design such a system, this system which has no temporal operators in it, then I would essentially be doing factorization, non-trivial factorization of numbers. And if we had an efficient way of doing this, then this would break the existing crypto systems, which really rely on the hardness of factorization. Right? So we know that designing these kinds of systems are not going to be easy. at one extreme, we saw that we can have an arbiter which doesn't even look at the input and just keeps flipping its outputs. That's really kind of the most naive design one can think of. But at the other extreme, we have things like this, where if we can really efficiently design this, this would actually end up doing large-scale disruption. So this is not going to be easy to design. So the spectrum really spans the whole thing. You have easy problems, you have easy but meaningful problems, an arbiter. You have unrealizable problems. There is no hope of always meeting the specification for every input that this environment provides. But even when things are unrealizable, it may still be useful. And so, it's really a very nuanced picture. Okay? So before I go to the next part, let me pause here and ask, are there any questions about, do we understand what synthesis is about and what are we up against? Right. So maybe if I can again ask Garvit, are you there? Garvit Gupta?
Yes, sir. I understood, sir.
Understood? Great. And then
So,
Mayank? Yeah, there's a question. Go ahead.
Yeah, so is it safe to say like any system where output depends on the future of unrealizable, or is there a system where like the output is depend on the future of and it is realizable? Is there any such example?
The output depends on the future inputs and it
It
is
is
realizable.
Yeah.
I mean, it depends on the specification, right? I mean, for example, if you say that the output at the current time step is either the input at the next time step or the negation of the input at the next time step, then of course it's realizable, right? So here the output, at least the specification is talking about a dependence of the output on the future of the input. So, what I'm saying is that I have shown you an example where I have, just in the interest of time, I have kept it so outrageously unrealizable that, you need to look into the future to make it, right? But I mean, here is another one, right? Here you don't need to look into the future, but still this is unrealizable, right? So it is not.
Okay.
So it is not that you only need to look into the future to get unrealizable, and it's not that whenever you need to look into the future, things are unrealizable. So it really depends on the specification. Right? Okay. Okay. So
I have a question.
yeah. Yes, please go ahead.
Yes, so in this method, you showed an ad hoc way to, well, let's say to classify that, okay, that system is unrealizable. So
Right.
if, let's say, a complex specification came in, then
Absolutely.
is there any formal way, or let's say
Yes.
a formal tool?
Yeah. So we are going to hopefully learn all of, at least some high level ideas of that. I don't
Okay.
know how much time we'll get to go into the depths, but yes, absolutely. So starting from actually, if it's a specification like this which has no temporal operators, all we are asking is, for all x, does there exist y? Right? So I can write a quantified formula asking, for all x exists y, this formula, exists y1, exists y2, this formula. And if that formula is true, then indeed for every x, there is a y1 and y2 that satisfies the requirements. And if that formula is false, it means that there is some x where there is no y1 and y2 which will satisfy the requirement. So, for a formula like this, which has no temporal operators and either bit vector or, it's really a vector of binary variables, this becomes asking a question in what is called quantified Boolean logic or quantified Boolean formula. And of course, there are algorithms which will tell you whether that quantified Boolean formula is true or false. In the case of LTL, we will see that there is actually a way, starting from a formula, we can actually, do something to it, and at the end of it, we can examine that and tell that whether there exists any solution at all or not. Okay? So yes, I mean, I have been talking in ad hoc ways because we have not yet got into the technicalities. But your question is very valid that we should have, and we cannot depend on these ad hoc ways to tell us whether something is unrealizable or not. And indeed, there are algorithmic ways to do it. Okay, did that answer your question? Who was it? Saurabh or somebody?
Yes, sir. Yes.
Okay,
Uh,
great. Okay, yeah, go ahead,
yeah, I have another question. So,
please.
I mean, the current framework that you described, yes, in that framework, yes, the second example was completely unrealizable. But are there ways to, I don't know, like characterize the environment so that, or characterize the environment so that there are no adversarial, I mean, that you can be sure that there are not going to be any adversarial inputs, and so you can make a system realizable.
Yeah. So that's a very interesting question. So what you're saying is that, I mean, this is kind of like an open system, right? I mean, this system is receiving inputs from an unspecified environment, and it is providing outputs to that unspecified environment.
Yeah.
So you're saying, can we say something about the environment itself? So
Yeah.
that would be something like a closed system. It's like two systems talking to each other, and you want one of those systems to behave well so that the other system can be designed.
Hmm.
Right? So yes,
Or maybe a system that encapsulates this system.
a system
That has.
Oh, so you're saying that okay, so if some bad input comes from the environment, that's a very nice idea. And while I don't think we will have time to cover that in today's lecture, but that is, in the literature, that is called a shield synthesis. It's also a synthesis problem. Basically, when you realize that, exactly the problem that you said, that there are adversarial inputs that can come from the environment, and your system may end up doing things that violate the specification. You want to build a shield, right? So you want to say that, okay, if such things come, I'm going to transform them minimally so that the system still doesn't do anything which violates the environment, which violates overall specification.
Excuse me,
Right.
sir.
Yeah.
Am I audible? Hello?
Yeah, go ahead.
Sir, but if you are doing such transformation, you are changing input itself.
Yes,
so it's no more the X value which was given to the system.
absolutely.
So, I mean, you are not satisfying the requirement.
Very good point.
Like
So
that.
yeah. So a very good point. What I was saying is that there is this problem of a shield synthesis, right? I'm no longer synthesizing. So that problem says that I have given you a system. The system is given to me, and the system, violates some requirements if certain bad inputs come to it. Okay, and those requirements are for the system. So you think about this as, this specification is talking about the relation between its inputs and its outputs, right? Now, if I put a shield in between, the actual environment is interacting with the shield. The shield is producing some inputs over here, and then it is producing some output, and you can again put a shield again on the output over here, such that it generates the final thing that the environment sees, right? So if you're given a system and you know that that system is not going to satisfy the required specification between its inputs and its outputs, you can perhaps wrap that system around with certain shields, which will satisfy some other desired specification between the actual inputs going into the environment and the coming from the environment and the actual outputs going into the environment. Right? So shield synthesis is usually used when you already have a system, but it's not doing exactly what you wanted it to do. So you put layers at its inputs and outputs such that you constrain the behavior of the system, such that at least for the environment it's doing what. But if this was your specification in terms of the environment, then there is nothing that you can do. Because this specification, the environment is saying that I want to see a y1 which will match the next value of the input x that I will produce, then of course there is nothing that you can do, right? But the shield synthesis case is where you have an internal system and you had an internal specification for it, and that system was not satisfying that specification. But there is an specification, there is a separate specification at the environment level. You know what the environment expects the relation between its inputs and its outputs. And instead of designing a system completely from scratch, you can take an existing system, build shields around it, and repurpose it for the specification for the environment that you had. Does that answer your question?
Question. Yeah.
Yeah, but if the specification in terms of the environment's inputs and outputs are themselves unrealizable, there's really nothing that you can do. I mean, the environment is something that you don't have a control over. I mean, the only other thing that you can do is to not make the environment completely uncontrollable. Because typically, you know, what happens is when you're designing such systems, these are part of a much larger system, and this is perhaps taking its input from the output of something else, and this is giving its output to the input of something else, and eventually something is interacting with the real environment. So it may be possible for you to say that, okay, whatever component is generating the outputs here, it should not do something which makes it difficult for this system to be designed. And what it is doing at its output should not make it difficult for whatever the next block is trying to do. Right? So typically these are smaller components within a system, and the environment of this system could be actually the output of the outputs and the inputs of other systems, other subsystems. But if the specification at the level of the overall environment is unrealizable, then there is nothing we can do. The overall environment is indeed uncontrollable.
Apart from this LTL spec, can't we?
Can you speak a bit louder? I can't hear you.
Can you hear me now?
Very faintly.
No. Okay. Maybe we can take this question later.
Yeah. Yeah, I can hear you better now. Yeah.
Okay, so apart from this logical LTL spec that we have, we know that for certain inputs, the system can be, let's say, not realizable for certain inputs, right?
For certain inputs, there is no way of generating the outputs. Yeah.
Yes. So, apart from this LTL spec, can't we put some, let's say, constraint on the spec itself that okay, this for these inputs, the system is unrealizable for rest of the inputs? Okay.
Yeah. I mean, you can change your spec, right? Remember, the spec is just, so if I go back to my first slide, the spec is just a formula on which has the inputs and outputs as the free variables, right? So your spec can indeed say something about the inputs also. Okay, in fact, in the afternoon when we look at using a tool, so typically, you know, okay, so let me, yeah, I should find a better way of doing this. Yeah, just open the slides in journal itself. Yeah, can you see my screen?
Yes, we can.
Yeah. So you know, I mean, yeah. So so typically what you have is you have, I mean, this is a typical design scenario that you have a system that you want to design, and there are some inputs that it is receiving, and there are some outputs that it is generating. And typically you will have some assumptions on these inputs. Okay. And typically you will have some guarantees that you will require, right? So this assumption on the input could be a formula phi on the x's, and this guarantee is usually another formula, or maybe I've used phi. So let's say this is a formula alpha on the x's, and this is our formula phi on x and y. Right. So typically our the specification we want to synthesize is that alpha x implies phi xy. So this is the specification that we would want to synthesize. This would be the specification when I'm trying to synthesize this block, right? So that all that this block is going to guarantee is that if alpha x is true, then phi of xy will be true. But you can look at this entire formula itself as some phi prime of x and y. Right? If alpha, for example, is an LTL formula, phi is an LTL formula, alpha x implies phi xy is another LTL formula. And that you can look at the specification of the phi prime specification for your system to be designed over here. Right? So you can, in a typical design environment, you will have assumptions on the inputs, and we will see this in the afternoon when we play with the hands-on session, when we play with the tool, that it will allow you to put assumptions, and it will allow you to specify guarantees, because this is very easy, right? I mean, I can just write it like this, and this is another temporal logic formula, and I'll just do my synthesis with respect to this. So if anything that violates alpha x, automatically the specification is satisfied. I mean, if alpha x is false, I mean, you would have learned on the first day, right, that when you have an implication and the left-hand side is false, it doesn't matter whether the right-hand side is false or true, the implication is true. Right? So this is the typical setting. What we are going to study today is that you have been given a certain phi prime, and after that you have no control. That phi prime may already have factored in some assumptions on the inputs, may not have factored in, that we are sort of blinding ourselves to. We are just told that we are given a temporal logic formula or whatever, a bit vector formula or a propositional formula on inputs and outputs, and our goal is to synthesize that, right? Does this make sense? Because now, if some inputs x come which violate, and let us say that phi xy was unrealizable, but phi prime xy is realizable. And now I synthesize a system which satisfies phi prime xy. Phi xy, of course, is unrealizable, so it cannot be synthesized. But now, if the environment provides some inputs that violate alpha, phi prime xy is still satisfied, because if alpha x is false, then alpha x implies phi xy is true already. Right? False would imply anything. Does this make sense? Saurabh?
Yes, sir, it makes sense.
Yeah. Rohan, you wanted to ask something?
Sir, I wanted to ask that, formula is like alpha x implies to phi x comma y, right?
Yeah.
Okay.
Yeah, I mean, if you're given assumptions on the inputs and you want to, establish the guarantee only under those assumptions, then you create the spec for the system that you want to design by factoring in the assumptions. You say that I want this to be true. So only when alpha x is true, I care about phi xy being true. If alpha x is false, I don't care.
Understood, sir.
Okay, great. So yeah, let me. I think I will. But it's good. I think it's very important we have the discussions, because it's pointless talking about things. At least we should understand a little bit of what we can cover. Okay. Let me try to go ahead now. I hope everybody has a reasonable idea of what is the synthesis problem we are trying to sort of address, and of course there are multiple nuances of it. Okay, so I also want to sort of use some terminology here, sort of establish some terminology here. So there are two kinds of systems that we saw in the examples. One where temporal operators were involved, like the arbiter and this unrealizable specification, and the other where no temporal operators were involved. So, and these actually correspond to two kinds of synthesis problems, at least as discussed in the literature. So the first kind, where temporal operators are involved, we are actually talking about a system and an environment that are always interacting with each other. Examples are like an operating system or a network switch or a plant controller, right? There's a continuous interaction going on between the system and the environment, and there is no meaningful end of computation. Of course, if the nuclear plant blows up, then of course everything ends. Or if the system crashes, or if you turn off the power, the operating system ends, or the network switch ends its computation. But there is no meaningful end of computation. Okay, so it's a continuous interaction happening, and the specification talks about the relation between inputs and outputs in this continuous interaction. So it talks about an infinite sequence of inputs and outputs and how they're related. I can use operators that look into the future in the specification. I can use operators that look into the past in the specification. So I can talk about, inputs and outputs as parts of sequences in my specification. And typically, we have been talking about LTL. We will see that. I think this was also briefly covered. I'll also cover it briefly today. You can also talk about what are things called automata over infinite words, to describe, to sort of present such specifications. And then there are the other kinds of systems which are like the factorization example I showed you, which are called functional synthesis, where the system generates outputs in response to the current inputs only. There's no dependence on past history. There is a meaningful end of computation. Some inputs are given, you generate some outputs, that's it. Okay. Again, if you give some inputs, again it will generate some outputs. And the relation is only between the current inputs and the current outputs. Right? So these you can express using propositional logic, bit vector logic, or whatever, maybe integer arithmetic. And no temporal operators are needed because we're only talking about current inputs and outputs. And this is also a very rich area of work that's out there. For example, program synthesis, and these are programs, not the programs that go inside an operating system that are continuously meant to run. These are like functions. They have some preconditions, post conditions, and you want to synthesize the function. It will take some input satisfying the precondition, generate some output satisfying the post condition. Arithmetic computation, numerical computation. And what we will see hopefully by the end of today, that actually this can also be used to synthesize the next state logic of reactive controllers. Remember, here we said that we're going to talk about mealy machines. So these mealy machines would require some next state logic and some output logic. So functional synthesis can also be used for that purpose. Okay. So that's kind of like what are we trying to do. Okay. And I have around 5 minutes left. So what I want to do is to maybe chart out a very high level outline of what is it that we're going to do in the next sessions that we have. So Shubhajit, 10:30 we are supposed to stop, right?
Yeah, it's 10:30, but again it's little flexible, Supratik. So you can decide, like we want somewhere like
no, I think that's okay. So maybe
Sure.
what I will do is so let me just present the very high level picture, and then we'll take a break, and then we'll come back, and then I will really use the journal thing after that to sort of explain each of the steps.
Sure, awesome.
So what we will do from now onwards is mostly talking about reactive synthesis from LTL specs. And okay, so I will cover the LTL basics and all after the break. But here is the very high level steps that we need to go through. Okay, and let me spend a couple of minutes on this so that when we meet on the other side of the break, then we know exactly where we are. I mean, this is kind of like our roadmap for at least the next session. Okay, so we will start off with an LTL formula. This may have assumptions factored in, this may not have assumptions factored in, none of our concern. We're going to start off with an LTL formula. Okay. And then what the first step that we will do is we'll actually convert it to an automaton. So I believe on day one, you were already told about this result, that every LTL formula can be converted into what's called a non-deterministic Bookey automaton. So I will try to go through this very briefly. So this was covered. Does anybody remember this from the first day? Maybe if I can get a few responses, I'll know how much time to spend on it. Does anybody remember conversion?
Yeah, we did look at LTL, and I don't think we spoke in detail about non-deterministic Buki automaton. It was mentioned, and we did see how it is useful, but I don't think we went into the specifications or explanations of it.
Okay. Okay.
But
So
we
once
saw examples in case of non-deterministic Buki automaton. We saw examples like how can we convert.
Great. So you know what a non-deterministic Buki automaton is, right? I'm presuming all of you know what a non-deterministic Buki automaton is. I will sort of spend maybe 5 minutes on it or 10 minutes on it, but I'm going to presume that you have already seen some non-deterministic Buki automata before, and that's not going to come as a complete surprise. So what we will do is we will take an LTL formula phi and we will first convert it to a non-deterministic Buki automaton. What I mean by that is, a Buki automaton basically accepts infinite sequences of letters, infinite words. And when we say we are going to convert it, we mean that every infinite sequence of input and output valuations that satisfies this formula will be accepted by this Buki automaton, and every infinite sequence of input and output valuations that this Buki automaton accepts will satisfy this formula. Okay, so we'll have this. Now, why are we doing this? This is at least historically, this is how the synthesis problem has been solved from LTL formula, and this is still predominantly how it is solved. I mean, there are the tool that we're going to look at in the afternoon actually bypasses this step. It goes directly from the first to the third step, and it uses some very, very clever ideas to do that. I do not know if I'll have enough time to talk about it, but we'll certainly see it in action when we run the tool in the afternoon. But the whole idea is that I want to take a formula phi and I want to convert it into our goal is really to convert it into a game. You can think of the synthesis problem as a game between the environment and the system. The environment is providing some inputs, the system is providing some outputs. Again, the environment is providing some inputs, the system is providing some outputs. The environment's goal is to make the system violate the specification, and the system's goal is to produce outputs such that it can always satisfy the specification. So it's really a game. The synthesis problem is exactly a game. Now, so once we come to this point where we have, you don't need to worry about what this parity means. Our goal is to convert this formula phi into a game, and en route we'll have to go through this non-deterministic Buki automaton. As I said, recent work actually bypasses this step and directly generates this. Now, once we have this game, there are very, very nice algorithms which can tell you, particularly for the kind of games that we're going to talk about, parity game, which can tell you exactly the question of unrealizability. That the game is being played between the system and the environment. So once I have this game, I can algorithmically answer, is it possible for the system to win this game? Okay. And if it is not possible for the system to win this game, it means the formula was unrealizable. The environment can always force the system to break the specification. And if it is possible for the system to win this game, then there is something called a winning strategy. And there might be multiple ways of winning this game. And there's something called a winning strategy. I mean, there could be multiple winning strategies, but what we will do is we will try to extract one winning strategy, at least one winning strategy. And of course, depending on, I mean, we have seen in the arbiter example, one winning strategy is just flip between y1 is 1 and y2 is 1, right? That is one winning strategy. Maybe another winning strategy is to say that, okay, the moment you see r1 is 1, set y1 is 1. But that has a little bit of a problem, because if both r1 and r2 simultaneously become 1, you don't want to make y1 and y2 simultaneously 1. So you have to prioritize them. So you have to say that, well, whenever r1 is 1, maybe I'll set y1 is 1. And if r1 is not 1 and r2 is 1, maybe I'll set y2 is 1. So there are different kinds of strategies that you can do to satisfy the formula and therefore to win the game. And of course, which strategy you're choosing here decides, the quality of the solution that you're getting. We are probably not going to be able to get into that today about choosing between different possible winning strategies. We'll just show how to extract one winning strategy. And then once we have extracted the winning strategy, we have to construct a Mealy machine out of it. And once again, here we can see that functional synthesis may again play a role there. So this is roughly the, the sequence that we will talk about. And on the other side of the break, we will start with, so some of these constructions are very, very involved, particularly, for example, from non-deterministic Boki to deterministic parity. It's very, very involved. So I'm not sure if much is going to be gained by going through all of that construction here, but we'll look at some examples, and we'll hopefully try to get the overall idea of what is going on, right? And then, of course, we'll see hands-on in the afternoon how all of this is used. Okay, so I will stop here.